We have found in our earlier discussions that memory is a very important component in embedded systems. Today, we shall look at different types of memory and how they can be used. Let's recapitulate our concept about the memory and its usage in an embedded system as well as in a general computer. So we can view that CPU and the main memory as a big array of bytes, and that basically is my microcontroller or a computer. We can also put in an in-between memory controller to interface with external I/O devices as well as memory. In fact, we have seen a number of these processors or processing cores targeted for embedded system have memory interface units provided for this purpose. So the basic structure or the organization is something like this. I have got the CPU. CPU is interfaced with directly here with the memory. There will be an address bus to select the memory location, bidirectional data bus for sending the data to write onto the memory as well as to get data from memory for the purpose of reading. These are the control signals, read, write, as well as this is a ready signal. If the memory is not being able to respond to the request, it may ask the CPU to wait. So that's why another interfacing signal is a ready signal. The size indicates the number of bytes that are expected to be transferred through one read or write cycle. So effectively, a memory access, what we call, is a bus transaction, and the bus transaction or the nature of the bus transaction can be in many cases defined by a finite state machine. So here we are showing how this decoding can take place. There will be address, it will be decoded, and individual words in the memory will be selected. Memories come in many shapes and sizes, and the technology changes. This is a cartoon which says that today I can have a technology with certain features, but tomorrow it may change drastically. And this is true with memory, with continuous evolution in the technologies that are going into their manufacturing. Basically, we have this broad categorization: RAM, random access memory; ROM, read-only memory; EEPROM or flash, electrically programmable read-only memory. But it is interesting to note that ROM as well as EEPROM and flash, they enable random access. That means you can access any location in the memory and you did not access them serially or sequentially. Further, we can look at their divisions into dynamic RAM, DRAM, static RAM, that is SRAM, ROM or flash, which are read-only memory, and read-only is often used for bootstrapping. In fact, flash has got some characteristics so that we can even do in circuit writing as well. So they are not strictly read-only, but their primary usage in applications may be for read-only purposes. Here we have got a comparison of their characteristics. In fact, dynamic random access memory is very dense and consequently inexpensive. But it requires refresh. Why it requires refresh? We shall understand when we look at its structure. Static random access memory is first, no refresh is required, but it is not as dense as that of dynamic random access memory. And often it is used for cache or other applications where we require really fast memory. What do we mean by density of the memory? It is actually the area that is required on the silicon real estate for implementation of a single bit. When we see DRAM is more dense than that of SRAM, we mean that the area required for implementation of a single bit of DRAM is much less. Let's first look at static RAM. A typical static RAM cell, that is a single bit implementation, is something like this. It requires about 6 transistors for its implementation. You can understand that this back-to-back inverter actually forms a flip-flop. So the bit is retained in terms of the states of this flip-flop. So when you read a data, what you do, you select the row. So this is your select word or row select line. You select the row. Selecting the row means effectively you are activating these transistors, and you sense this bit bar and bit line. Okay, these two lines are actually fed to what we call a sense amplifier. So the difference in their currents is actually sensed to read the data. So on the other hand, how do you write? You drive bit lines and select row, and accordingly what you do, you force the flip-flop to change state if it is required. So this is how a bit gets stored in a static RAM. Obviously, since it requires 6 transistors to implement a single cell, the area required for implementation of a single bit SRAM is more. This is a simplified SRAM timing diagram. That means how the signals should be sent or received from the static RAM for the purpose of reading and writing. So here we are using a very simplified form where we have got this write enable. So when it is an active low signal, when it is high, that means we are basically doing a read. The chip select is basically selecting the corresponding IC or the memory module for the purpose of reading. The address is provided on the bus. The decoder would be typically part of the memory device itself for selecting the row. So that means once I have selected the corresponding memory module and I have provided the valid address, the row would be selected. And after that, you will expecting the data. So this is the time difference between the address becoming valid and you receiving the valid data. So read is valid address, then chip select, access time, address good to valid data. Even if it is not visible on out, that means it may take some time to get it visible because there may be output buffers. So this is basically a critical parameter to estimate performance of a particular memory block that you are using. Access time smaller means the memory is faster. Now in this case, what we are showing is you are making basically write. So valid address is there, data is also valid, your write enable is validated, and then you have got the chip select, and then you actually write the data. So what it says that address must be stable a setup time before write enable and CS goes low, because address has to be valid for the purpose of selection. So there has to be a setup time between the write enable and CS to go low, and hold time after it goes high. So this is basically the hold time. So what we say, this is the memory cycle time, the minimum time between subsequent memory operations, because I cannot have a new address put in. I cannot have a new address put in before expiry of a memory cycle time if I am doing a write or a read operation. Now let's look this timing in more detail. So this is a typical scenario where I have also assumed that there is at the output stage and buffer, a 3-state buffer. So one of the state is a tri-state high impedance state, and I have got the output enable signal which enables the output buffer. So here we have got more timing parameters which I have shown in this context. So what you have got here is you have got the address which is shown here as a basic stable part, and here we are showing the data which is coming out as a valid data, because I am now looking at primarily the read timing, okay, and this output enable. So when there is output enable low, you actually are getting the valid data. We shall now look at specific definitions of these different parameters. So TAA is called access time for address. How long it takes to get stable output after a change in address. Next is access time for chip select. How long it takes to get stable output after CS is asserted. TOE, it is the output enable time. How long it takes for the 3-state output buffers to leave the high impedance state when OE and CS are both asserted. So you have found that I have now refined the definition of access time. The access time definition now we are providing with respect to address as well as with respect to chip select, and a parameter is being defined with respect to the output enable signal as well. This is the TOZ, which is output disable time. How long it takes for the 3-state output buffers to enter high impedance state after OE or CS are negated. And TOH is the output hold time, how long the output data remains valid after a change to the address inputs. Now these parameters that I have discussed in detail are primarily read timing parameters. Now what is their importance? Now if I am connecting a processor to a RAM memory block for the purpose of reading and writing, obviously, the timings have to be consistent, and these parameters determine the speed at which I can really read data from the RAM or write data onto the RAM. Now we also have seen that we have got SRAM which are already embedded inside a microcontroller chip, and when such an SRAM gets embedded into a microcontroller chip, basically the designer has taken care of all these timing requirements. So you have got a compatible memory on chip. Externally, when you are interfacing, your selection of memory block has to be dependent on these parameters, and that will also dictate the speed at which external transactions can take place. Typical feature of an embedded SRAM would be obviously low density, because I am using 6 transistors per bit, and high speed. And this is a preferred choice for frequently accessed and time critical storage like cache memory and register files. And in fact, you have seen like in processors like PIC, your entire memory is organized as a register file, and there this would be basically static RAM. But wherever you are using static RAM, power is always a serious concern, because in an embedded system we would like to minimize usage of power. In a static RAM, what are the source of power loss or the power consumption? One is static power loss due to leakage, because you have seen the transistors on the path, okay? So there will be a leakage current even when you are not actually accessing that memory, because that memory is in an active state. It is storing the data that you have stored. So there would be a leakage current, and that is what we call a static power loss. Then there will be a power consumption, what we call a dynamic power consumption, due to switching of long and heavily loaded beat and word lines. Because these beat and word lines are connected from cell to cell. Obviously, I shall need current to drive these beat and word lines to provide me the correct data. So there will be switch, dynamic power consumption. That current will be driven into those lines when I am actually selecting or reading a word from the memory or writing a word into the memory. Also the sense amplifiers, which comes into play when you are reading out, their speed also depends on the power that they are consuming. So these two components actually account for power consumption by the SRAM. So power is always a serious concern when you are using SRAM in an embedded system. So there are various technologies which have been developed to minimize power consumption but not sacrificing the speed. Next thing that we have seen, that in many embedded processors, in DSP processors as well, there are multi-ported memory. So obvious motivation in any kind of a pipelined processor, which are the processors which today we find to be find them in many of these SoCs and embedded systems, are pipeline processors. So if I have one read or write per cycle, it can limit processor's performance. It also complicates the pipelining, because it becomes difficult for different instructions to simultaneously read or register file or on-chip memory. So a very common arrangement is for pipeline CPUs to be provided with 2 read ports and 1 write port associated with the memory. So you can see that we have got in some cases dual access memory, single access memory. In dual access memory, they are basically 2 read ports and 1 write port is a common arrangement. So there are simultaneous reads from the memory block. So effectively, what does that mean? If I am talking about a multi-port or dual port, effectively it means that I am having additional decoders. The 2 decoders, because there can be now address coming from 2 distinct buses, because there can be 2 simultaneous read access from a memory block. So there are 2 distinct decoders and another set of read-write logic, bits lines and word lines. So you have got these 2 distinct data ports. So this is where the read-write logic will come in. And in this case, the picture is something like this. You have got the same inverter, okay, and now you have got, in this case, say 2 bit lines. These are bit and bit bars, okay. So you can have simultaneous access, because I can sense B2 and B2 bar and read the data. Similarly, B1 and B1 bar and read the data from this cell. So I have got now dual ported read access from SRAM. In fact, dual ported memories are very common in SoCs and on-chip memories for various DSP processors. As well as registers. The register bank implementations are also through this kind of dual ported SRAMs. Next, we look at dynamic RAM. So SRAM cells exhibit high speed but poor density. So DRAMs are expected to have high density. Why high density? Because they are actually using a simple MOS capacitance to store data. In fact, the charge stored in the MOS capacitance would be indicative of the data that is being stored there. So simple transistor capacitor pair, that's what we have shown here, and this is the basic structure of the cell. So you find that this is much less space consuming, okay. But the only problem is I need to refresh it at regular intervals. Why I need to refresh it at regular intervals? If I am storing charge in the capacitance, the charge will leak out, okay. So I need to refresh the charge on this capacitance at regular interval. So it is not that once write and forgotten forever. Just like SRAM, as long as the power is on, the data would be retained. But this is not true for dynamic RAM, because charge can get leaked out, so it is needed to be refreshed at regular intervals. The organization is typically something like this. So you have got, here we are showing a simple example. So what do we say? The DW total bits are organized as D supercells of size W bits. So it is a kind of a row column organization. So each cell now has got a row address and has got a column address. And the CPU generates the address which goes to the memory controller. Once it receives the address, the memory controller generates separately the row address and the column address to access the data which is stored in a particular cell. So let us see how the reading really takes place. First, you have to activate what is called row access strobe. Okay? So if I am reading, an example is I am reading the data from the cell 2-1. So you activate the row access strobe, which selects your row 2. So this gets selected, this is a particular row, gets selected on the basis of this signal. Next is the row 2 is copied from DRAM array to row buffer. So this will be copied to the row buffer. Now the interesting thing is that the row as a whole gets copied. Okay, so in the buffer you have got data about not only a single cell but multiple cells. So now I have to select a particular cell using the column address. So I shall activate the control signal, which is column access strobe. So this column access strobe, okay, is activated now, and what is to be noted is that in this case this address pass is being multiplexed between row address and column address. So on the basis of this column address, you select the internal cell, and where do you select that cell? You select that cell in the row buffer, and then that copied from buffer to data lines and eventually back to the CPU. So this gets copied to the data line, and then it goes from here to the CPU via memory controller. This is a typical read operation for DRAM. Similar is your write operation, and in fact read operation has got another interesting feature to note, that the refresh operation is normally nothing but dummy read. If I do a dummy read, I can actually refresh the cells. How is that memory really organized? So here I am showing a 64 MB memory module consisting of 8M into 8 DRAMs. So you generate the address, address is row and column J, so effectively all these cells actually gets selected. Once it gets selected, you provide those bits, okay, you have provided row as well as a column address. So these cells will provide these bits, okay, and all these bits together will constitute the 64 bit or a double word at a memory address A, and then this will be sent to the CPU. So what is typically being shown is how multiple DRAM modules can be organized together to provide you a double word or a 64 bit with data word, double word data for the CPU. Now let us look at DRAM timing parameters. Obviously these timing parameters would be related to RAS and cache signals. TRAC is a minimum time from RAS line falling to the valid data output. Okay. So if it is it is quoted as the speed of a DRAM when you buy. This is T, that is minimum time from RAS line falling to get the valid data output. A typical 4 MB DRAM TRAC could be 60 nanoseconds. TRC is a minimum time from the start of one row access to the start of the next. That means when I have accessed one row, okay, and then I have to access the another row, there has to be a definite delay or the time period or the cycle, and these values typically 110 nanosecond for 4 MB mbit rather DRAM with TRAC of 60 nanoseconds. Then you have got minimum time for the CAS line falling to valid data output. Okay, so falling actually we are telling that is activating. So it is, we are considering all these RAS and CAS as active low. So it is 15 nanoseconds for 4 MB DRAM with TRAC of 60 nanoseconds. Is a typically order of the timings. And TPC is a minimum time from the start of one column access to the start of the next. Okay. So you can see therefore the time taken for a data access for the DRAM will be more, because you have to give time for the row access and then the column access. There are a variety of enhanced DRAMs which have been proposed recently, and you should understand what is the motivation for these kind of technology developments. The whole access of DRAM is based on two asynchronous signals which are RAS and CAS, and they are not really synchronized with the bus clock, okay, because once the address is provided, okay, to the memory controller, these RAS and CAS signals are being generated, and then with respect to RAS and CAS, your row address and column address have to be put in to access the data. Now, variations of these to speed up the DRAM access have been suggested, which is synchronous DRAM or SDRAM. And in fact, in many of the PCs and others today, when you buy memories, you buy SDRAM. So it says that the RAM is driven, the control signal is based on the rising clock age instead of asynchronous control signals, that is RAS and CAS. So SDRAM is tied to system clock or the bus clock and designed to be able to read or write from memory in burst mode after the initial read or write latency at one clock cycle per access. So you do not need what is called wait states, because if RAS and CAS are asynchronous signals and they are generated by the memory controller, so the time taken to get the data would be more than the bus clock or the clock at which the system, or the system clock, the clock at which the system operates. So system would need to wait to get the data from the DRAM, and that's why the wait states can get inserted. But if now these RAMs can be made synchronized with the bus clock or the system clock, then the wait state requirement can be eliminated, and that is the basic motivation of designing the synchronous DRAM. An improvement on that is double data rate synchronous DRAM, this enhancement of SDRAM that uses both clock edges as control signals. The key feature that you should note here is that we say that data is being accessed in burst mode after initial latency. Okay, that means multiple data is obtained, okay, so that you are effectively accessing one data item per clock cycle. Fine. How that can happen? This can happen because if I am able to get multiple bytes, that is, once I select a row, I am actually selecting multiple cells on that row. So I can also get multiple data from that row. So that's a basic intuition behind designing burst mode access to these DRAMs. So obviously when we have embedded DRAM going on to SoCs, it is primarily for providing high density storage, although it is significantly slower than SRAM. And another difficulty is it requires dedicated process for on-chip fabrication, because it is not really compatible with the standard CMOS technology which goes into fabrication of your logic modules, which are your processors and peripheral controllers. Next, we have non-volatile memory. Mask ROM are typically used for dedicated functionality, and it is once programmable ROM basically. So, contents are fixed at the fabrication time itself. EEPROM are erasable as well as programmable, and they require some special IC process because it's based on what is called floating gate technology. Okay, this is again a MOS technology and floating gate technology. Here the writing is slower than RAM, and it uses special programming system to provide special voltages and timing. Reading can be made fairly fast, but rewriting is slow because you have to erase. And you typically talk in terms of UV light exposure for eraser for EEPROM, and electrical erasable modules are called EEPROM. Flash is a variant of this EEPROM. So, what is the basic technology goes into them? The concept is that of what we call floating gate MOS, and it is effectively a single transistor, okay, and just like we say in DRAM, we use a capacitance to store charge as indicative of the data. The same thing is true here as well. All these modern EEPROM, electrical erasable PROM, and flash memories are built around this technology. There is an additional floating gate in these transistors. This floating gate is surrounded by silicon dioxide, which is an excellent insulator. Okay? So, if this gate is charged, then charge will not strictly flow out or leak out. By controlling the terminal voltage, it is possible to charge electrically the floating gate, and that is why you require special voltages to write onto these chips. Okay? And obviously, there has been enhancements and circuitry going in, making them electrically erasable in terms of each bit or each block. So, the basic technology is that of floating gate MOS. So, what you can observe and realize that here also a single bit is requiring area that of a single transistor. So, the storage density for this kind of non-volatile memory will also be more than that of SRAM. So, electrically erasable PROM are erased using higher than normal voltage, because then you can force the charge to flow out and this charge can be rewritten. Can be erased by words and not in entirety. What does that mean? Not the entire memory area has to be cleared, but each word can be cleared. It is in circuit programmable, and these are the typical times for EEPROM. The flash memory again uses a single transistor bead. Electrical EEPROM employs two transistors, more than one transistor. A flash memory provides high density storage with speed marginally less than that of SRAMs. Speed is primarily with reference to access or the read time. The write time is significantly higher compared to DRAM. So, they are electrically erasable, but the interesting thing is they are erasable in terms of sectors, variable size sectors in a flash. The basic difference between electrically erasable PROM and flash is that in electrically erasable PROM you can erase each word individually, but here it is block erasable typically. There are two kinds of flash which are available, which are called NAND flash or NOR flash, depending on actually the way the cells are organized. So, you can understand here, this is a typical NAND organization of the cell. Okay? This is an individual cell and they are all connected to the common source access point. This is basically the contact point, and this is a NAND organization of the flash. And this is a NOR organization of the flash. So, you can realize that connectivity pattern is such that NAND flash would require smaller size for a fixed amount of storage. So, you have got small chip size. In many cases, microcontrollers use NOR flash. So, here the area required is typically more. So, And where are these embedded non-volatile storage used in embedded system? Obviously, they are used for storing configuration information. Also, the executable code that runs on these processors are in most cases stored on this non-volatile memory area. Now, this gives you can realize the higher read bandwidths and less pinout requirements. Why? Because you do not need an external memory. So, what is being compared here, if you are having your program running on an external memory block vis-a-vis the program being stored in a one chip flash or any other form of non-volatile memory. So, you can have higher read bandwidths, okay, and your pinout requirement goes low. You can have application specific tailoring of bit width and memory size, because you do not need to have it compatible with available chips, flash chips and their configurations. The other interesting thing which is important is security of proprietary code. Since it is sitting inside the code, it becomes difficult to access and know what the code is all about, and then do some kind of basically forgery in the sense of taking the code and using it for other purposes. Other thing is that recorded data, typically your voice recorders, your cameras, they all use flash, which actually enable repeated write. Current these FGMOS based memories can withstand more than 10 to the power 6 rewrites, and even other observation is that once charged, they can actually, the charge leakage time can be as large as 10 years. So, that is why many of these recorded data, that when you have a speech recorder or a camera, you actually have these flash cards to store the data, or the flash memory to store the recorded data. Now, we shall see that once we have got these types of memory, we shall now see an example of interfacing these memories, okay, with the microcontrollers that we had already studied. In particular, we shall look at ARM. So, if we look at ARM system architecture, go back to the ARM system architecture, obviously I have got on chip RAM, okay, and we know how to use, we need to know how to use this on chip RAM, but we can also have external RAM to be connected to the system. The whole idea here is that when we are interfacing external memory units, we should know how to use the signals which are being provided by the processor core. Now, this is important when we are building up a system in terms of discrete components. This is important even when we are building an SoC, because when I am building an SoC, I have what? I have got this ARM core as a specification, and I know what kind of signals are being provided by the core. So, if I am developing a memory module to be used in my SoC, that memory module has to be compatible with the signals that are being provided by the processor core. So, we shall look at ARM7 memory interface signals. In fact, we had already looked at them, we are just reviewing it again for the sake of completeness. It has got a 32-bit address bus, it has got 32-bit bidirectional data bus, as well as separate data in and data out bus. So, that means depending on your requirements, you can connect your memory modules to these buses. Now, a very obvious thing would be that if you are just putting in a ROM where you do not need to write, okay, a non-volatile storage where you do not need to write, you may connect it directly onto the data in bus, and if you are connecting a RAM, that would be typically connected to, typically to a bidirectional bus. Although if it supports separately data in and data out bus, if the external memory supports explicitly data in and data out lines, then you can connect it here as well. But many of the memory modules have got a single bidirectional data interfaces. These M request and ACQ, these are two signals, okay. This is an active low signal M request. This actually indicates whether your ARM core is requesting memory access or it is requesting sequential memory access. Now, this point we shall see that how to use this signal for having an efficient access when we are interfacing with external memory. Read write are for read write indication. This one we will look at the size. If you remember, we started the basic model where we had size as a signal. So, this signal, this is a 2-bit signal because it indicates the different sizes. So, this indicates the size of the data which is to be transferred over the bus. And these all activities are to be synchronized with regard to the MCLK, that is the system clock. Now, here you can find out that the clock control has got associated with it a signal called wait bar. This is an active low signal. In fact, your internal clock for the processor core is actually combination of the two. And how and where to use this wait signal? If you remember, I said that in many cases my memory may be slow. When my memory is slow, for a memory access, the processor has to wait. So, the memory module has to tell the processor that you please wait till I provide the data. Okay. So, in that case, this wait signal becomes important. So, that is why I am telling that your internal clocking or internal operation is controlled through a combination of MCLK and wait signal. Let us see how we can connect a simple SRAM and a ROM module. This is a typical ARM core, and this is a control logic that I can build. I can connect these SRAMs. These are all 8-bit SRAMs, okay, and these are all 8-bit ROMs. Now, what we have seen here, that write enabled, these SRAMs are write enabled separately. So, that means typically here I have got individual write enable signals. The individual write enable signals are not coming from the ARM core, that is to be generated by the interfacing logic which is here, okay. And here what you are finding, this address is going to all of them, and what I have shown here is that your address is provided to all these SRAMs, okay, and their read enables, the read enables are all enabled together, okay. So, what we are telling is that read enabled together, but write enabled separately. Similarly, in case of this ROM, no write enable signal is required because I do not need to write to them, and they should be read enabled together. Now, here what you will find is that we have shown typically, if you see the address buses, the addresses the way it has gone in, that this is a 32-bit address, okay, and this 32-bit address is fed to the controller as well as to the these RAMs, because this address have to be decoded by these RAMs to select the individual rows. The decoding logic is part of this SRAM module, okay, and this is being fed here. And the reason why you say that the last 2 bits are not being used, because if they are all located, if these are all 32-bit word data, and if there are byte addresses and they have to be located at a 32-bit boundary, then last 2 bits actually becomes redundant, okay. And this is a common this data bus to which both RAMs are connected, okay. So, effectively it is in terms of 32 bits. Now, next question comes, how do you design this control? When I am designing this control, what I have to do? I have to use various control signals which this ARM core is producing. okay, and that control signal have to be used. So this is a simple example of a control signal. Now this control can be implemented on an FPGA or may be implemented in terms of a discrete logic. If it is really going into a SOC, this becomes part of the SOC. So the interesting thing to note is I control activation of RAM and ROM. So A31 bit is typically being used for this purpose. So if you see here, A31 bit is being used for selecting RAM or ROM, obviously because they are located at two different addresses. They have to be located at two distinct partitions. Now the other interesting thing is that this one, what we have got is this mass 1000 byte, 01 word, half word, 10 is word. Now these signals are being fed here, and the logic is with regard to the different RAM write signals. That means depending on the size of access, that means I may like to write a byte at a word location, okay. So if I am writing a byte, then I am activating a particular RAM. If I am writing 16 bit, I shall activate two of them. So that's why the size signal becomes important, and this is coordinated with your MCLK signal, because what we say that all these things have to be valid, okay, ROM enable when the address is valid, and this signal gets validated with respect to your basic clock which is driving the system. Is this clear? So now these addresses are, these addresses if you see A0 and A1 which were not being fed to the individual memory blocks, they are actually being used for selection of which signal to enable, okay. That is depending on the size of the transaction, and depending on this address, one or more of these RAM write enable signals will be activated, okay. And this is a way by which your size information has to be made use of, because you need to know for a bus transaction what is the size of the data transfer that is taking place. So address should be stable during the falling edge of output enable. The SRAM is fast, but ROM is slow, and ROM needs more time. It slows the system. So what we are trying to say is that the access time for the ROM is slow. Now that provision we have not shown that how to take care of the slow access time of the ROM. Now the whole thing needs to be modified to take care of the slow access time of ROM. So obvious thing is use wait states. That means when you are using a ROM access, you have to use the wait signal so that the system can wait. Now, so let's take an example. So where ROM access requires 4 clock cycles and the RAM access is faster. Now obviously in this case the bus transaction, the control logic for the bus transaction has to be captured by this FSM. So what we say that if I am starting, so this FSM goes into where? This FSM is actually will go into implementation of the control logic. So if it is a first, so if it is a RAM, so I shall be always in the first mode. If it is not so, if it is on the ROM, I have to take care of 4 states. So my wait signal should be low, okay, if it is an active low for 4 states, so that the system should wait till it gets the data from the ROM. So this is basically my control logic defining FSM. But now let's look at this timing diagram. So effectively what we are telling, this wait goes low here, okay, and this ROM enable has to be active for this time period, because these are the 4 cycles which is required for the access. So this is now the timing diagram that would be there when I am using a ROM which is requiring 4 clock cycles for an access. how does the processor operates? Do we really need the processor to wait? Because my processor is actually a pipelined processor, because there would be other instructions which can be executed, and when I am looking for this data from the ROM, because ROM can actually have what? The instructions, the programs. So while one instruction is fetched, other instructions are getting executed. So processor internal operation cycles do not need access to memory, and in that case the processor performance is not going to suffer. Okay, that is something which is important. Only wait states will get inserted when the processor explicitly requesting the memory access. So that is the basic significance of this aim request signal which is coming out of the processor. Okay. So aim request 0 clearly indicates the memory access, and aim request 1 is a internal operation. So when it is aim request 0, okay, so effectively what it means, I go to the RAM decode, I go to the RAM and come back, and when I am doing the access here, it is a ROM access, fine, and corresponding to that there will be the wait state which would be generated. So actually this aim request signal indicates that at what point the wait should be really made active, okay, when we are doing a ROM access. Then let us look at this DRAM access.
So what do we mean by internal operation?
The question is, what do I mean by the internal operation? Internal operation means it is when it is executing instructions, say ARM, it requires registers which are involved in the operation. So it does not require a memory access. So that operation can continue without the memory access. So it is not that ROM access would make the processor always suffering 4 wait states. So it is indicating through memory request that it is now going into a memory access cycle. So that memory access part of it can wait because it is accessing the ROM. So let us look at the DRAM and the question of interfacing DRAM with ARM. We are just recapping the DRAM organization. You have first row address. The first row address is presented and latched by RAS signal. Next column address is presented and latched by cache signal. This is what we have already seen. Now how to do that with ARM? Does it have any spatial signal to facilitate DRAM access? Now how can I make DRAM access faster? Okay. Accessing data in the same row using cache only, access is 2 to 3 times faster because you are not paying for the row access time. Okay. So cache only access does not activate the what we call the complete cell matrix. If next access is within the same row, a new column address may be presented just by applying a cache only access. And this exploits the fact that most processor addresses are sequential. If I am not really executing a branch, okay, I shall be accessing addresses in a sequential fashion. If I am accessing addresses in a sequential fashion, then I can have a much faster access from DRAM. Okay? And particularly if I have my DRAM for storing the data, if I am accessing say data blocks like an array, okay, in a particular fashion and in a disciplined fashion, then I shall be accessing them sequentially. So what we shall do, that if we had a way of knowing that the next address is sequential with respect to the current address, then we would only assert cache and make DRAM access fast. So I need to know this next access is a sequential access, and so I need to detect early in the memory access cycle the next address is in the same row. Okay, and for that the sequence signal, ACQ signal, which comes out of the ARM is a ideal source of that information. So sequential addresses are flagged by ACQ signal which comes out of the ARM. Fine. So the external memory device checks the previous address and row boundaries to issue cache only or RAS cache combination. Because all sequential addresses cannot be satisfied by simply cache only, because I may go from one row to another row. So memory device controller will decide whether to generate only cache or to generate both RAS and cache. So effectively my this finite state machine that which defines a controller for bus transaction would look something like this. So depending on whether it is sequential or not, so this is the sequential when I am doing here. So effectively I know that in this state I shall activate what? The cache only case and or RAS cache depending on the condition. Otherwise, when it's a ROM access, I have to go into a wait state, and particularly when there is a memory request. So the timing diagram would look now something like this. So in fact, it is a pipelined memory access. So if I have a pipeline memory access, typically address is presented half cycle earlier. Okay, so what you have got here is this is your clock, the system clock, and these are the addresses which are being provided, and here you find that the address is coming earlier, okay, so that you can know that next is a sequential address. Then this sequential, this one is activated. This wait state comes in because there will be a wait when it's a RAS cache access, okay, wait for a RAS cache access, and wait is asserted by the external logic. So when it knows that there is a sequential access, the wait need not be low. You have the RAS remains valid all through, and what you are having? You are asserting cache with different column addresses. You are asserting cache with different column addresses, and so you are getting the data from consecutive locations. And this is precisely the reason why the ARM processor core provided ACQ as an output signal. But you can understand that the way to use these signals for actual interfacing, you need to implement the interfacing logic. So this comes to the end, this brings us to the end of today's lecture. We have learnt about different types of memory and their characteristics. We have seen how external memory can be interfaced in ARM 7 based system. We shall next study memory management and use of memory, because use of memory is a very critical issue in the context of embedded systems, because I have to have limited memory and I need to know how to use that limited memory effectively in the future classes.